Geraldo,
Yes.
we're live now.
Okay, can you get started?
Yes.
Okay. So, welcome everyone to the last class on computer architecture in this whole semester. I hope everyone had fun on the exam yesterday, particularly the great big question that I prepared. Um, but today we are going to have some cutting edge research topics again to finalize the semester. I'm going to start with some three back-to-back papers related to processing memory. In particular, those three presentations are focusing on the MEM system that we discussed during the class that Dr. Juan Gomez Luna presented during the lecture. So I'm going to be talking about some of the work that he conducted or he led uh, related to some challenge or some issues that the mapping system has and the way that we managed to solve them. So I'm going to start with this work that was published in ISPAS last year, TransPimLib, Efficient Transcendental Functions for Processing Memory Systems. And so let's get started. If we have questions on YouTube or if you have questions on the class, please feel free to stop me at any point. Okay, so as usual, executive summary, as you probably should know by this time during the semester, processing memory is a promising solution that can be used to alleviate data movement bottlenecks in many modern applications. However, the types of hardware that you have available when you want to implement processing memory computing is quite limited because of the cost of including logic together with computation. And this makes it difficult to have a broad or complex instruction set architecture. And how this impacts applications, and in particular, in this work over here, we are focusing on the effect that it has on transcendental functions. So the transcendental functions are functions that you cannot approximate easily using arithmetic operations. So you can think about sine, cosine, trigonometric functions, logarithmic functions, and also other how to implement complex functions, like for example, square root. So these functions are quite important, those because they are quite used in many applications. As for example, many machine learning applications that are you have a lot of, for example, sigmoids that use exponential functions, for example, or in transformers in LLMs, you have the use of sine cosine, for example, for positional encoding. So our goal in this work is to mitigate this problem or find a way to implement those complex operations, those transcendental functions inside the memory system using alternative methods. And we came up with this library that's called TransPimLib that uses two different methods to approximate transcendental functions. So the first one is a for-based method, and the second one is a lookup table-based method. And based on that, we implement sine, cosine, hyperbolic functions, logarithmic, square root, and so on and so forth. So our code is publicly available in your GitHub repository, so you can check over there. And then we implement and evaluate the performance that TransPimLib have in terms of several metrics for several micro benchmarks and also for three real-world applications, black hole, sigmoid, and softmax. So this is the outline for this talk. I'm going to give a really brief overview on process memory. At this point in the semester, it shouldn't be a surprise to you what process memory is and also translation functions. Then I'm going to talk about the TransPimLib library and then a quick evaluation. So let's get started with process memory. So as you know, process memory advocates for moving data or computing where the data resides. So moving computing elements nearby the memory arrays themselves. And right now is a great time to think about process memory because we are starting to see the first real commercial available process memory systems from industry. So in this class, we talk a lot about the UPM system. We also talked about the Samsung HBL system, the XD, the XM Hynix, and the Alibaba ones. And actually, that is more common. So this year in the Hot Chip 2023 conference, Samsung announced at least three different, I think three, don't quote me on this number, but I believe three other follow-up systems that build on the Samsung HBM architecture for cloud and for more um, hardware restrained devices like mobile phones, for example. So process memory systems are coming, and they are hoping in the future going to become a de facto accelerator for data movement bottlenecks. So what is common across those process memory systems is that it has a host processor. So we are not advocating to replace the host processor to process memory systems. And this host processor has a standard main memory and a process memory enabled main memory. The process memory enabled memory contain multiple process memory units, and this process memory unit can enjoy high memory bandwidth and low memory access in general. And those processing units, PIM processing memory units, they are a bit different than the host processor processing elements because they operate at few hundred megahertz. Because, as I said earlier, manufacturing computation together with memory imposes some challenges, and it's hard to clock the PIM units at really high clock speed. And at the same time, they have small number of registers or small number of cache or fetch memory. And usually, process memory unit communicates with the host processor via the host. So this is just a figure of that system that I just described. So you have the whole system, you have the standard memory, you have the process memory enabled memory, which is composed of several cores. The several cores have some memory bank and some special path memory. So in this work, we're going to use the UpMem architecture, which uses general purpose process memory cores called DPUs. They can run up to 24 PIM threads called testflets, and they support natively 32-bit integer arithmetic, but other operations like multiplication and divisions and float point operations are emulated. And also, the UpMem system has each DPU has access to a 64 megabyte DRAM bank called MRAM and a 64 kilobyte scratchpad memory called WRAM. So let's say that you want to calculate a sign function in a process memory system. How would you do that? So there are three alternatives to do so. So the first one would be to have a special hardware unit inside the process memory core to calculate the translational function. So in this diagram here, for example, the host offloads some computation to the PIM core. The PIM core, when it encounters a transcendental function, offloads that computation to the translational unit. And then when the computation is done, the computation resumes the PIM kernel and then moves back to the host kernel, and everything is done. So this is one way, which incurs hardware costs. The second way would be to offload the computation back to the host CPU because mother processor has processing engines designed specifically to accelerate or to compute translational functions. So you can use that. So you offload some computation to the PIM kernel, and when the PIM kernel is done, and encounter translation functions, you offload that translational computation to the host CPU, and then you offload the output of that computation to the PIM kernel and then to the host CPU back. This goes against the purpose of computing where the data resides because you are having this extra data movement over here between the PIM kernel and the CPU. And the last way of doing so is by having some way of computing translational functions inside the PIM cores themselves. So here the host offloads some PIM current to the PIM cores, and then the PIM cores themselves have some way of manipulating, calculating translational functions using its own instruction set architecture. And then when this computation is done, the PIM kernel continues, and then when the computation is done, is moved to the host CPU. So note that this saves both area because you're not adding a translational unit, and saves execution time because you're not incurring more data movement between the PIM kernel and the host CPU. So in this work, we propose TransPimLib, which is an open source library that implements those translational functions inside the PIM cores of the BEM system. So let's see how TransPimLib is implemented. So there are various methods to calculate translational functions. For example, Taylor approximations, minimax polynomials, coordinates, and table-based methods. So in this work, we focus on coordinates and fuzzy lookup tables, since those methods have low usage of floating point multiplications, which is, as I said earlier, are emulated in the PIM system that we are using. So the The coordinate method, the first one that we implemented, is an iterative method that uses only bit shift, addition, and table lookups to calculate presentational functions. And it involves some error, right? Because you are basically, you're trying to approximate that computation. So the maximum error when using coordinate shrinks exponentially with the number of iterations that the coordinate algorithm implements. So in this particular work, we use a coordinate implementation in what's called a rotation mode, which computes a function, for example, a sine cosine for a given input, for example, a angle theta. The algorithm works by starting with that angle theta and an initial vector, in this case here, a vector of coordinates 1 and 0. So each iteration of the algorithm, we update the theta and rotate the vector by multiplying by a 2x2 matrix that represents the rotation angle. So the second method is what's called a fuzzy lookup table. Lookup tables are quite used for many years already to generate different functions, specifically from the implementation of functions. So if you look at the history of embedded systems in particular, they use they suffer the same problem as of these systems, that like implementing those translational functions is quite hard, quite costly in terms of hardware. So it's quite common that they use the fuzzy approximation methods, fuzzy lookups to implement or to approximate translational functions. However, since the lookup tables are limited in size, it's not always possible to return the exact output value for each single value of an angle, for example. And this is where the fuzzy comes. So fuzzy here being approximate method for the particular input or particular angle that you want. So how this works? So for a given input, x, we obtain an output that approximates the original function in 2 steps. So in the first step, we use a function, we call it here a of z, or of x, sorry, that returns an address. So then we use this address to query the lookup table. For example, this x function may be just simply rounding up the numbers, and then we are using that round up number to access the table. So in the second step, we access the lookup table with the address, as I said. So one commonly way to improve lookup table accuracy is to use interpolation. This is quite interesting. If you look at the, it's either the SK Hynix one or the Alibaba one, I don't recall exactly right now. But they use this the same method of lookup table interpolation to improve to approximate or to improve the accuracy of sigmoid, if I'm not mistaken. So it's as I mentioned that just to say that this is a common approach across this type of thing. So TransPimLib contains also the core implementation of several of those translational functions, sine, cosine, and also hyperbolic functions, sine of h, cosine of h, tan of h, exponentiation, logarithmic, square root. So we illustrate how TransPimLib, the coordinate method works using a sine function. So here I have the flow diagram of implementing the sine function inside the FMM system. So first, we translate the input value, so for example, angle, to a limit range between 0 and pi and 2 pi. Second, if the input is in floating point value, we convert it back to a fixed point format. So our first fixed point format uses 28 bit for the fractional part and a 3 bit for the integer part, which is enough to represent 2 pi, 2 times pi, and 1 bit for sine. Third, the range is further reduced to the range from 0 over pi over 2, so we can have one of the 4 quadrants in the, if you think about the circle of angles, basically we are looking at the first quadrant over there. So 4, because it repeats, right? Fourth, the coordinate algorithms iterate until it obtains a sign of the input angle that you are looking for. Then fifth, we adjust the sign value based on the gradient of the input angle, so moving back to the two times pi. And sixth, and finally, we convert the output value back to a float point format, and then you have your output. So TransPimLib implements several lookup table-based methods. So those are the second ways of implement those translational functions that basically differs on how you generate the address that I mentioned earlier for the lookup table query. So the first method that we use is the multiplication-based lookup table method, which defines regular state between table entries. So there are some math related to over here. So I'm going to not go so much into details, but basically what you are using here to calculate the address is the round of the input minus p times k, and where k and p are constant. So k in particular represents the density of the lookup table, which is the inverse of the statement that you have available, and p defines what value x corresponds to address 0 in the lookup table. So the n-loot address generation needs one subtraction only, on multiplication, and one step of rounding or truncation. So it can be cheap to implement in the optimum system other than the multiplication. So let's say that we, for example, want to map some values from the range 0 to 5 to a 12-entry lookup table using the m-loop method. So in this case here, for example, we can use k equals to 12 over 5, which is 2.4, and p equals to 5 over 2 over 12, which is 0.2. Does I input x, for example, equal to 3, translates to an address a of 3 that goes um, to 7. So, and here you can see the density of that. So the density of a value of 3, for example, give a density value of 2.4 for the 0 to 5 interval that we're taking the picture. So the second method here is what is called the LDX based method. So as I mentioned earlier, right, multiplication is generally quite expensive in the implementing system, but we can make it cheaper. But if you instead of multiplying by any number, you multiply by 2 to n. So to do this transformation, you use a function called LDX, which is common in many math libraries to perform the operation of arg times 2 to the exponent that is the input. So for the LLoop method, we define the address generation function that loses some freedom to design the lookup table, since the density of k must be a power of 2, but now you are avoiding the multiplication. So this results in the LLoop of lower precision than the M-loop, but extends to the range of to further range. So here you can have a range from 0 to 6 instead of a range from 0 to 5. So the third method is what we call direct float point conversion based lookup table. And this is based on the observation that a good spacing depends on the approximated functions to minimize the output error that you're going to have. So this may need nonlinear address generation, which are generally more computationally expensive than multiplication. So we mitigate this issue by exploiting the natural nonlinearity of float point format. So basically here, we are going to use a address generation function that uses the last n bits of the exponent of a float point number and the p bits of the mantissa to generate the address. So this results in a piecewise linear density with 2 to the n steps of 2 to the p address each. So the density of each step is inversely proportional to the input value. So higher densities for small input and lower densities for leads to larger input. So for example, over here, for our 12-entry lookup table, we can have n equal to 2 and p equal to 2. And then we are going to have a density in 4 for ranges from 1 to 2, a density in 2 for ranges to 2 to 4, and then a density to 1 for input values from 4 to 8. So in addition to the previous method that I mentioned, we also combine those methods to try to mitigate those their particular weakness. So the first combination is the direct float point conversions plus the LDX exponent based loop that I mentioned earlier. So this basically combines this combination basically shows the limitation of the out of the direct float point conversion. So for example, no entries between the smaller exponent and 0 by combining it with the dilute and the LLoop method. So the second one is a combination of the coordinate method plus the LDX exponent based fuzzy lookup table. And in this combination over here, we are replacing the first two iterations of the core deck computation with a lookup table. So this basically provides us with a flexible trade-off between the computation on cost, the table size, and the precision within the bounds of a core method and a core lookup table-based method. So based on this, all of those implementation methods, we implement several transcendental functions. In this particular work here, we are implementing sine, cosine, tangent, the inverse of all of those, exponential, logarithm, square root, and GLU. So as you can see in the table here, there are some particular methods that are not suitable for the particular function that we are using. For example, the tangent here we don't implement using with the GLU plus interpolation method. So now entering the evaluation part. I don't know if there is any question on Newton or in the class. Otherwise, I'm going to go into the evaluation. Okay. So we evaluate the TransPimLib library on a real process memory system, which is the MEMP system. And the system contains a host CPU with 156 gigabytes of memory. 120 gigabytes of memory and 20 of MEMP DIMMs with 159 gigabytes of memory. In total, we have 2,545 pin cores that run at 350 megahertz. So we evaluate TransPimLib's coordinated lookup table methods and combinations of those implementations on a single pin system using micro benchmark in order to compare those methods in terms of performance, accuracy, setup time, and memory consumption. So our micro benchmark computes all of our implemented transcendental functions for elements of an array of 2 to the 16 float point values with a randomly generated. The pin cores move chunks of the array into the expected memory of the MEMP system and operate on each element. We implement also 3 full workloads that use the transcendental functions, and those workloads are Black Schools, which is a finance workload, Sigmoid, and software. And we compare their implementation with their CPU-only version. So let's get to the results. So we start with the performance. So in all of those plots, you're going to see that the x-axis over here is the error that the method provides and of the accuracy, and we are calculating that using root mean square absolute error. And then the y-axis is going to vary for the very number of the very implementations that we have for the particular transcendental function. And this result here is particular for the sine function. And we also have 2 different implementations of those functions using placing those are particular for the lookup table based method. So we place the lookup table either in the memory RAM, so in the DRAM banks, or in the WRAM, the scratchpad memory of the MEMP system. So we make several observations based on the micro benchmark for the time cosine. So the first one here in terms of performance is that the performance of the lookup table based method is independent of the accuracy that you want to obtain. And the execution cycles depends on the number of multiplications that you're going to have. So the lower the number of multiplications, the higher the performance. So the inverse of the execution cycle. So the fixed point versions of the LOOT implementation doubles the performance of the interpolation method that use the LOOT due to a faster fixed point multiplication that we're implementing. So also here we observe so make some observations about the coordinate methods. So the first observation is that the coordinate methods take more execution times, provide higher accuracy than the lookup table based method. So here in this plot, you can see that the coordinate accuracy decreases with each iteration of the coordinate algorithms. And when we replace the initial computations of the coordinate method with the lookup table base, we can have faster execution time. So also we can see in this plot here that at some point at around 2 to the 9, further increasing the lookup table size for this coordinate plus lookup table method increase the lookup table size or the coordinate iterations. But at the same time, you are not seeing improvements in accuracy. So also you see little difference in placing the lookup tables in the WRAM or in the working RAM of the preemptive system. So the first takeaway that you take over here is that they interpolate lookup table methods over the best trade-off in terms of performance and accuracy. Why is that? Because your lookup table based methods are quite efficient to execute in a PIM system because memory access are cheap, and they recall that this LDX exponentiation is changing the expensive multiplications to power of two multiplications, which are also cheap to implement. So we also measure the setup time, so the time that it takes to load the loop, for example, or to execute the core implementation for those different methods. Again, the x-axis here is the root mean square absolute error, and the y-axis the setup time. So for loop-based methods, the setup time increases with the lookup table size, and for the coordinate method, we have a flat setup time. So the takeaway here is that coordinate methods can provide higher overall performance than the lookup table-based methods, where the total number of transcendental functions in a workload is low. So the takeaway that we take from here is that the coordinate-based methods are preferable when the PIM kernel needs to execute only a few transcendental functions due to their low setup time. So in terms of memory consumption, we see that the accuracy of the non-interpolation method is limited by the available memory that you're going to use, and the memory consumption of the coordinate method does not increase exponentially in contrast with the lookup table-based method. Also, the interpolation method is an effective way of increasing the accuracy without increasing the lookup table size. So the takeaway that we take here is that interpolation lookup table methods offer a good trade-off in terms of accuracy, execution time, and memory consumption. However, the coordinate and coord plus loop methods are recommended for applications that require high accuracy where the available memory is limited. So in our paper, we have several other analyses. So for example, we have the analysis of the other supported functions. So all of these methods that I mentioned here were for design function. So in the paper have for the other ones. So we also have evaluations of range reduction and extension. Discussion and takeaways about the D-loop and DL loop methods, and all of that in our paper. So briefly, I'm going to mention the results of the real-world applications, and we are comparing that with 1 and 32 CPU core implementation. And we also have a PIM baseline which uses polynomial approximation instead of the other methods, the coordinate and the lookup table based methods that I mentioned. So here we have the result for the black spool. So we have here the execution time for 1 core, 32 cores in the CPU, polynomial in different cores, and then those M-loots, L-loots, and float point L-loot methods for the black spool algorithm. And you can see here that for black spool, the TransPimLib is 5 to 12 times faster than the PIM baseline, and the fixed point lookup table based method is 92% faster than the 32 thread CPU baseline. So we have similar observations for the SimpMod and the softmax implementations, which basically the TransPimLib method outperform the PIM baseline and shows that it can save further data movement traffic when compared to the CPU execution. So basically here we are showing that the method I mentioned earlier that executes or emulates transcendental function using the PIM ISA itself is a feasible method for the PIM for the PIM system that we are using. Because we are reducing data movement from PIM core to the CPU, and we are not incurring extra hardware on the PIM core at the same time. So I invite you to check our paper if you are interested on transcendental functions for PIM cores. And also, again, our source code is available in our GitHub setup. So in conclusion, PIM is as you know, is a promising way of eliminating data movement bottlenecks in the system. So, however, implementing complex operations like transcendental functions in constrained hardware can be complex. So in this work, we are using the ISA of the PIM system itself to implement transcendental functions using 2 different methods and coming up with a library that provides these functions to the user, and this library is available in GitHub. We evaluate several metrics: performance, accuracy, memory, and setup time for micro benchmarks in the implementation system, and also 3 real-world applications. And I guess this is all for this work over here. I don't know if there are any question over there on the YouTube for this work.
There seems to be no questions, Gerald, for now.
Okay, thanks, Jan. Okay, so if there's no questions, I'm going to go to the next presentation. Give me 1 second.
Geraldo, maybe if you can make it a bit faster, because I'm not sure if you are going to present the two papers.
Yes, that I expect the other two to go faster because the basically background is the same, so I can go really quick. But I want to cover them a little bit because it comment across the three works.
Sounds good. Thank you.
Let me just share my screen over here. Okay, so this other work again is targeting the implementing system, but now we are going to implement machine learning workload on the implementing system. So as probably you know, training machine learning is quite a machine learning algorithms is quite a costly process, which often leads to both compute boundness and memory boundness for the CPU-based or for processor-centric system. So twin systems can alleviate the memory boundness of those training the machine learning algorithms themselves. And in particular, the UpMem system can be used because in the UpMem system, you have a lot of memory capacity, which is one of the main requirements for training machine learning algorithms. So our goal is to understand the potential for modern PIM systems to accelerate classic machine learning training algorithms. And to do that, we implement 4 different applications in the UpMem system: linear regression, logistic regression, decision trees, and k-means clusters. And we evaluate them in terms of several metrics, in particular, quality, performance, and scaling. And we compare its performance to processor-centric versus CPU and GPU. So as just some key takeaways that we have from our analysis, or implementations of decision trees is 27 times faster than the CPU and 1.3 times faster than the GPU, while our implementation of the k-means algorithm is 2.8 times faster in the CPU and 3.2 times faster in the GPU. Again, our source code, everything that we did in this work is available online in our GitHub repository. And we evaluate those 4 workloads using a deep PIM system with more than 2,000 PIM cores. And based on this evaluation, we draw several takeaways and recommendations for machine learning workloads on general purpose process memory systems. So the outline of this talk, I'm going to briefly talk about machine learning workloads. I'm going to extremely briefly talk about PIM again, then the implementation of the machine learning workloads. Then I'm going to go to the evaluation for 4 different metrics, 3 different metrics. For quality metrics, analysis of PIM kernel, performance scaling compared to the CPU and GPU. So we start with machine learning workloads. So machine learning workloads are quite everywhere. So right now there is a really high hype related to deep learning, but here we are targeting classic machine learning workloads which are quite still heavily used, for example, in data mining tests and data analytics classes. And when you try to implement those machine learning workloads, we often encounter a lot of data movement between the memory and the processing engine during the training step because you require a really large data set to train, and I would say not good accuracy. So at the same time, the amount of computation that you do is not enough to amortize the cost of data movement because often they have a lower arithmetic intensity, low temporal locality, and irregular memory access pattern. So our goal is to study the performance of classic machine learning workload training in the PIM systems. And for that, we use 4 representative machine learning algorithms: linear regression, logistic regression, decision trees, and k-means. And we start our analysis by showing with a RawAlign model that all of those workloads are memory bound on the CPU on the CPU in the CPU implementation. So all of them are below the memory roof or either of the DRAM of the L3 cache in the CPU itself. So those are good candidates for process memory offloading. And again, the process memory system that we're going to use here is a real wood process memory architecture that has a host CPU, pin system, the pin system with pin cores, and the communication happening through the host CPU. Again, we are using the upmapping system, which uses general purpose process memory cores and 64 megabytes of DRAM bank and 64 kilobytes of scratchpad memory per pin core. So going to the implementation of those machine learning training workloads in the mapping system, we first analyzed to see what was the diversity in terms of applications that you are using, if you use those 4 applications over here. And we see that they are quite diverse in terms of memory access pattern, in terms of computational pattern, and also in terms of communication that they use. So basically, these 4 algorithms are a representative set that can indicate us the performance of the memory system for different classes of machine learning workloads. So we're starting with linear regression. So linear regression is a supervised learning algorithm where the predicted output variable has a linear relationship with the input value, right? And in this work, you are using the gradient descendant methods to find the minimal loss function for the linear regression algorithm. So basically, on the PIM, it's going to be common across the implementations, or PIM implementation divides the training set equally among the PIM cores, and ptrace computes dot product of rows and weights of to implement the linear regression algorithm. And then after that, each dot product value is compared to the output observed output value to compute the partial gradient value, and those values are reduced and sent to the host CPU. So we implement 4 different implementations of linear regression to evaluate the UpMem system. So the first one uses a float point unit, which again are emulated in the UpMem system. The second one replaces those float point units with 32-bit fixed precision units, so fixed point representation. The third one uses hybrid precision, so you use precision from 8 bits to 16 bits to 32 bits. And the last implementation uses a custom multiplication-based method, which builds multiplication using the native 8-bit multiplier inside the upmapping system. So the logistic regression, the other method, the machine learning method that we implement, which basically is a supervised learning algorithm used for classification. And it basically calculates the probability value for each input variable in the input vector. So here we are using the sigmoid function to map predicted values to probability. So again, our implementation follows the same workload distribution pattern as the linear regression. And over here, we implement 6 versions of logistic regression. So again, 1 version with float point implementation, 1 version with fixed point implementation, a version which will replace the sigmoid computation in the float point implementation with lookup table queries. And for that, we have lookup tables placed in the memory RAM and lookup tables placed in the working RAM of the memory system. Again, we have the hybrid method with lookup table placed in the WRAM, and again, for the custom base multiplication method with lookup tables placed in the working RAM. So decision trees is another classification method which partitions the feature space into leaves and predicts in which leaf a particular input is going to end up. Or implementation partitions the training set again across the twin cores and computes the partial homogeneous cores to evaluate the host split decision. So this is how the communication happens. The host sends command to the twin cores to split, commit the tree leaves to evaluate the split, and also to get the min max to query the values of a feature in that tree leaf. So decision trees are commit to maximize the memory bandwidth, and also you have a streaming memory access pattern, or this data layout basically ensures that the access or memory access is streaming the split leaf when you're evaluating the split between the training. So the final method is the k-means, which is a clustering algorithm. Again, we are splitting the dataset evenly across the process memory cores, and each pin thread is going to evaluate the centroid which is closer to each point of the training set. So then the host calculates the centroid and the coverage to the local optimum when the updated centroid coordinates are within a threshold. Basically, this is implementing an algorithm called Frobenius norm for the k-mean algorithms. So this is a dish of the algorithms that we're implementing and the important features of them. And then as the evaluation methodology, we are using synthetic and real data sets for each one of those four applications. I'm not going to go into them. And the system that's used is the same as before, the PMP system. And we compare now also with the A100 GPU. So we evaluate quality metrics, performance of the pin core, performance in scaling, and comparison to the CPU and GPU. So in terms of quality metric, we see that the training error for the float-point version of linear regression is the same as the CPU because they're using the same data representation. And when you move that to fixed precision, we see that the error becomes still remains low compared to the the float-point implementation. For the logistic regression, we see that the lookup table methods have the lower training error rate, and and also for the decision trees, we see that the training accuracy only is slightly lower than the CPU version. For the k-mean clusters, we see that they use the change names for to measure the clustering outputs of the k-mean clusters, and we see that that score is similar for the P and the CPU implementation. So basically, we're concluding here that even though you are applying some transformations in the data input set of the training algorithms with the P implementation, we see similar accuracy for all of the workloads compared to the CPU baseline using float point data representation. And then the analysis of the pin kernel. So we start with the linear regression. So in this plot here, we have the x-axis, the number of pin threads per pin core, and then the y-axis, we have the pin kernel execution time for the different implementations of the linear regression. So in the top, we have using float point 32 data for the training, and here we have using the integer 32, the hybrid precision, and the building multiplication method. So we make several observations. So the first one, and this is a common observation for many workloads running the MEM system, is that all version saturates at 11 or more pin threads, and this happens because you see that 11 pin threads is enough to fill up the pipeline of the pin cores. So we also see that the fixed point representation accelerates the kernel compared to the float point implementations by one order of magnitude. And this is happening again because float point is emulated in the MEM system. So the first takeaway that you draw over here is that workloads with arithmetic operations or data types that are not natively supported for the pin cores runs at low performance. So basically here, don't use float point numbers, for example. And our recommendation is to use fixed point representation if possible. So the second takeaway that we do is that for if you use a hybrid representation compared to the integer 32 representation, we get further performance improvement by 41%. So our take recommendation over here is to use quantization as much as possible to take advantage of the native hardware support that you have for the pin system. And if you use the multiplication, the custom multiplication method, we can have a further performance improvement of 21%, 25% compared to the hybrid precision implementation. So the third recommendation over here is to use is to leverage programmer expertise or better compilers to optimize the codes to use native instructions as much as possible. For the logistic regression, we see a similar trend. Sorry. So we see very high kernel time for the float point 32, but this time also we see high performance, high execution time for the integer 6-point base implementation of that same kernel, and this is basically due to the computation of the sigmoid function. So if you replace the sigmoid function, use lookup table methods, we see a 53% times faster or slower execution time compared to the in-32 version. So our fourth recommendation is that in those cross-memory systems, it's better to convert costly computation to memory access as much as possible, so you can reduce execution time. So on top of that, if you use the hybrid precision method, we see a 28% faster execution time compared to the inter-32 with using lookup table. And again, if you use our custom building lookup building multiplier, we see an extra 43% performance improvement. So in the paper, we have also the performance for the other algorithms, the logistic regression, the decision tree, and the k-means. They follow similar trends. And a common takeaway here is that the performance of all of the kernels saturated 11 cores, and also those applications becomes compute bound when you move to the mapping system. So the second takeaway that you take here is that even though those machine learning workloads are memory bound in the CPU system or GPU systems, they become compute bound when running in the pin cores, because basically in the pin core memory is faster than computation, so it fits. So the sixth recommendation is to maximize the utilization in the pin cores as much as possible to keep the pipelines busy and mitigate that compute problem. Again, we do some analysis, some strong scaling analysis by varying the number of pin cores for each one of those implementations. So each bar here is the execution time, and the line represents the speed up compared to the CPU baseline CPU. So basically, the takeaway that you take here is that the pin kernel time scales linearly with the number of pin cores that you are using, and we see linear overheads for communication between the whole CPU and the between pin cores and the whole CPU, and between the pin cores and across different pin cores through the whole CPU. So the third takeaway that you take over here is that machine learning training workloads which need large data sets largely benefit to processing memory cores. Even if the core needs to communicate via the host, the amount of data movement needed is tolerable, so it does not significantly impact execution time. Finally, we have some comparisons to the CPU for the linear regression, for the logistic regression, and we see basically here is that the pin versions are heavily bound by the operations that are not natively supported by the hardware. So basically, the float point implementation execution time is much higher than the GPU, for example. Oops. And by applying our optimizations, we can close the gap in execution time between the CPU and GPU implementations and the pin system implementation. When you see the comparison with the decision tree and the k-means, we see that the decision tree is 27 times faster in the CPU and 1.34 times faster in the GPU, and the k-mean algorithm is 2.8 times faster in the CPU and 3.2 times faster in the GPU version. So in your longer version of our paper in archive, you can find more things, including the additional implementation details of all of those 4 algorithms, have more evaluation results, and also extended observations and takeaways that we draw based on the observation. So this is just some further analysis that we did comparing decision trees and k-means with even further I have a larger, basically, data set of 1 terabyte. So basically, this does not fit in the implement system. You need to iterate over many times. So the takeaway that you take here is that when the data set increases a lot, or performance is further increases and becomes better compared to the CPU and the GPU, because we are minimizing the data movement as even further. So for example, the decision tree implementations of the ping version leads to a 62 times better performance in the CPU and 4.5 times faster performance in the GPU. And we see a similar trend comparing to the k-means. So basically, the takeaway that we draw over here is that machine learning workloads that require many operations that are supported by the PIM hardware, like decision trees and k-means, outperforms their CPU and GPU counterparts. So, or again, our source code for all of those for implementation of those workloads are available in our GitHub repository. And in conclusion, training machine learning workloads it can be a memory bound problem depending on the data set that you are using. Process memory is a way of alleviating these data movement bottlenecks, and our goal is to understand the potential of real process memory systems to accelerate those shared machine learning training algorithms. To that, we implement four applications: linear regression, logistic regression, decision trees, and k-means. We provide several optimizations for the implementation of those algorithms, and we see that the PIM system cannot perform the CPU and GPU counterpart for applications like decision trees and k-means. And our source code is available in your repository. And we do some analysis based on the PIM system of those four applications, and we draw several takeaway and recommendations based on our analysis. And this is the end of this second talk. I guess I was a bit faster than the first one. Again, is there any questions related to this work on YouTube or in class?
No, please go ahead, Geraldo.
Okay, so let's go to the final one. This one. This one. Okay, this third work again is related to the MEM system, but now we are targeting a different problem. Now we are targeting programmability. So this work was presented in PAC this year and called SimplePIM, a software framework for productive and efficient process memory. So again, as a quick summary, process memory alleviates data movement bottlenecks. Reopening hardware is now available. However, programming this new hardware is quite challenging because it requires the programmer to have some knowledge of the underlying hardware device itself and to partition the data and the computation across that organization of the PIM hardware, manage manually transfer between hosts and PIM cores, and also across PIM cores, launch the PIM cores, the PIM kernel across the PIM cores, and which also requires to understand like the level of parallelism that the PIM kernel, the PIM cores also process. So basically, we are trying to alleviate this programming burden that the PIM system imposes to programmers by encapsulating or abstracting away all of those three things that the programmer needs to do. And we came up with this framework called SimplePIM, which is a high-level programming framework for real PIM architecture. So the SimplePIM basically works on iterators, as for example, map, reduce, and zip. And also we provide some APIs to allow the user to easily broadcast, scatter, and gather data across the process memory cores. So we implement, we develop SimplePIM targeting the PIM system, and we evaluate it against 6 different workloads. So those are reduction, vector addition with histogram, linear logistic regression, and k-means. And we see in evaluation that SimplePIM reduces the number of codes that required to implement those algorithms by 4.4 times. And we also implement some optimizations on top of our library that lead us to 15 to 40% faster execution time for some of those workloads. Again, SimplePIM is publicly available in your GitHub setup repository. So in this is the outline for this talk. I'm going to start talking about PIM and also how you program the real PIM systems. Then I'm going to introduce SimplePIM and then our evaluation. So again, it starts with PIM. I guess I don't need to talk about this again. PIM move data to computing units nearby the PIM, the memory device itself. Real world PIM systems have become real. They have those PIM systems have some common characteristics. We are targeting the PIM system, and Okay, this is the interesting part. So how you program the mapping system, right? We had a lecture on this in this semester, but just to remember to refresh your memory. So if you want to implement for example, a histogram algorithm using the UpMem SDK, there are several tests that the user needs to do. So the first one, you need to reset the heap. It needs to initialize the variable for the histogram population, allocate buffer space in the scratchpad memory of the system, double check the boundaries of the memory accesses so that it does not spill across different banks in the mem system. We need to load the scratchpad memory with a block of memory from the RAM, and then you finally need to do the histogram calculation. Besides all of that, you also need to put some synchronization barrier for the pin port synchronize and merging the histograms for the different threads or test class in the UpMem system into one histogram in the GPU, and then write back the result in the trackpad memory to the DRAM in the UpMem in the pin memory itself. So as you see, there is a lot of code that is required to manage the computation. So the only thing that the user actually wants to do is to calculate the histogram. So the only thing that the user were interested was this line here, histogram calling histogram function. But there are many other lines of code over here that the user needs to manually write down to manage the data across the updating system, and also to synchronize the computation and communication across the process memory cores. So basically, this is a downstream text and there's a challenging text that requires the user to manage fine-grained data movement from the host in the pin cores. Also, the data movement inside the process memory cores themselves, and also to program the pin system thinking on multi-threaded programming mode execution, which leads to synchronization. The need to include synchronization primitives, which are not always trivial. So our goal basically here is to design a framework that can abstract away those hardware specific details on programming the UpMem system and provide an interface that can use the programmability of that system itself. And then we came up with SimplePIM, which is a high-level programming framework for process memory. So our software framework, SimplePIM, leverages the massive memory bandwidth and parallelism offered by the PIM hardware to operate on arrays of arbitrary sizes and dimensions. So SimplePIM offers three key interfaces to support PIM systems like the PIM system. The management interface stores metadata for the PIM resident arrays, which can be accessed by the programmer and by other parts of the SimplePIM as needed. The communication interface provides abstractions for the host ping and the ping from ping to ping communication. And these patterns are similar to communication patterns in other distributed systems like MPI, which makes it easier for SimplePIM to be adopted. Third, the processing interface leverages the ping core high memory bandwidth and parallelism to execute some common execution patterns, those being map, reduce, and zip on pin array. So programmers can combine these iterators to implement many widely used workloads, ranging from simple vector addition to complex machine learning model training. So let's check which one of those interfaces. Start with the management interface. So the management interface is going to store metadata for pin resident arrays. So we have here two metadata, the array metadata, which describes the pin resident array, and the SimplePIM management, which for managing those arrays themselves. So there are three main operations that can be performed on those pin arrays. The first one is the retrieval as the lookup, which basically retrieves relevant information of an array. Register, which is register the metadata for a given array, and free, which basically removes the metadata for a given array. So then we have the communication interface. So the communication interface basically manages host to ping and ping to ping communication. So the first one being the broadcast communication pattern, which transfers the array in the host memory to across all of the ping cores in the system. And here is a picture on how the broadcast is happening. The second communication primitive is a scatter gather primitive, which the scatter one distributes array to to the pin DRAM bank, and the gather primitives collect portions of array from the pin DRAM banks. And I guess this is an illustration of how the scatter and gather operation works for example input array. And then we have pin-to-pin communication primitive. So this is the there are two of them. The first one is the R-reduced primitive. We use it for synchronization, and the programmer basically here is specifying accumulation function that when the synchronization happens, when the accumulation finishes, the synchronization would so when the function finishes, the synchronization barrier is reached. So the other one is the altogether, which basically combines all of the pieces of array distributed across the pin systems to complete array and distribute this array across all of the pin ports. So basically here we are gathering all arrays spread across all of the pin ports into a single array and distributing those single array across all of the process memory cores. Then we have the computing pattern primitive that we are using, and those are again three, right? Map, zip, map, reduce, and zip. So to map array, basically you're applying a function to every single element of the input array itself. And the important thing here is that the input size and the output size are exactly the same. The second one is the reduction, which applies a transformation functions to elements of the input array, generating an output index. So here, basically, you have a function that is applied to all of the inputs, and all of the inputs are accumulated in a second function and generated an output of size different from the input. Then you have the zip operation, which is the one that takes two input arrays and combine them, implementing to an output array. So here we have the example, we have two input arrays. The zip function is basically compressed, it's not compressing, but it's merging those two input arrays into an output array. So on top of all of those APIs, we also implement several optimizations that we are known to lead to better performance in the APIM system when generating the code for the binary for the application itself. So those being strength reduction, loop unrolling, avoiding boundary checks, function inlining, adjusting of data size, and adjusting of data transfer size. And all of that, if you're interested in all those, I invite you to check our paper. So our evaluation, again, we are using the real mapping system, and we are implementing several applications using the SimplePIM framework. And then we compare SimplePIM and with versions with the hand optimized code in terms of performance and programming productivity. So this is, again, the hand optimized histogram example that I showed earlier. So you can see the 9 lines of code that are used over here. And this is the SimplePIM version. So basically, the SimplePIM encapsulates several of the functions. For example, the programmers first define the histogram specific functions in a file, then the accumulation function, the map function that's going to apply to the values in the array, and then you issue the host side handling to iterate over the input array, transfer the data, and finally run the application itself. So you can see here that is fewer lines of code than the previous implementation. So when you compare the line of code reduction for those 6 workloads from a hand optimized version, you see a reduction in line of code from 2.98 times to 5.93 times. Then we perform some weak and strong scaling analysis of those 6 workloads for different systems. So here we have different numbers of pin cores and the y-axis execution time. Then we have the SimplePIM version and the host the hand optimized version for those workloads. So in terms of performance, we see that we have comparable performance for 3 applications and for the performance improvement for vector addition, logistic regression, and k-means, but for up to 37%. When you do a strong scaling analysis, we see that the SimplePIM scales better than the hand optimized implementations for some algorithms, and it can further outperform some of those algorithms by up to 43%. Some discussion related to SimplePIM. So even though we are devising SimplePIM for the upcoming system, this framework can be generalized to all the process memory PIM system where the host processor and the PIM system uh, uh, are disjoint. So it's a loose couple accelerator method, and the PIM system communicates to the host CPU. And the number of PIM systems is still with the memory capacity. So basically, this can all be generalizable. Another thing that SimplePIM emulates the communication between PIM cores via the host processor, because the PIM system does not enable direct communication between the PIM cores themselves. And other parallel patterns like prefix sum and filtering can be easily adopted in future work. Also, extension and convolutions could be adopted, but access patterns that require random access is a bit hard to support because it's hard to generalize in a single primitive. Again, in our paper, we have a further discussion of those challenges for in future work for SimplePIM. Again, SimplePIM is publicly available in our GitHub repository. So in conclusion, basically this work is trying to deal with the problem that programming real PIM systems, in particular the PIM system, is quite challenging because the programmer needs to have knowledge of the underlying hardware itself and needs to manually distribute data across the PIM cores, manage data, and also launch the PIM kernel directly. To solve this issue, we propose SimplePIM, which is a high-level programming framework for the PIM system, which encapsulates several of those routines into simple APIs that the user can use to improve programmability. We implement SimplePIM with 6 different workloads, and we see 4.5 times fewer lines of code compared to hand-optimized versions, and up to 450 times performance improvement for pure workload. Again, SimplePIM is available on the GitHub setup. So this was, I guess, since this is the last lecture of the semester on process memory, or not like not this one, because you're going to have another talk related to PIM. But I invite you to, if you are interested and curious about process memory, I invite you to look at our Modern Prime Process Memory book chapter available in our website. And over there, you're going to see a review of other types of process memory cores, and also the challenging and of adopting those process memory cores in the future. And hopefully this motivates all of you to do great research on process memory, which is again a great time to do so with this push from industry, and also the push from the application domain as well. So I guess that was all from my part. Thanks so much for listening, and I don't know if there's any question in the audience.
Thanks a lot, Geraldo. Seems there is no question.
Thanks so much, Mohammed.
Yeah. So we're gonna have a break until 2:30. Thank you.
Can you hear me on Zoom? Yes, all right, perfect. Yeah, then let's get started with the fourth presentation today. Hi everyone, I'm Joel. I'm a second-year PhD student in Safari. I'm going to present to you two of our bioinformatics works. The first one here is SeGraM, a universal hardware accelerator for genomic sequence-to-graph and sequence-to-sequence mapping. Let's dive right in. I think you've seen some of that background before, but for the sake of clarity in sequence-to-graph mapping, I'll repeat it in my own illustrated way again. So we can do genomic sequencing, and this enables a bunch of applications such as personalized medicine, outbreak tracing, or understanding of evolution, science. And the modern sequencing machines that we have, they extract only small fragments from the full DNA molecules. So we need to do this read mapping. It changes quite heavily depending on the technology used. So you get either short sequences with small error rates or very long sequences with fairly big error rates. Our algorithms need to adapt to that. Now, this is classically done to a linear reference genome. So we call this sequence-to-sequence mapping. So we have a read and a single linear reference. Yeah? So a string, when I say a linear reference, that's a string. And what we do in this work is a graph-based reference. So we do sequence-to-graph mapping. The sequence being the read and the graph being the reference. The reason why we want to be doing this in the first place is that graphs enable us to get some quality improvements in the mapping. So somehow in terms of the end-to-end application, mapping to a graph gives us better results, but from the computational side, it's a more challenging problem to do it both well, efficiently, and quickly. And yeah, part of that is it makes accelerator design more challenging. So at the time when we were working on this, there was actually no prior hardware design for this at all. So our goal here is, well, to achieve a whole bunch of superlatives with this work. We want a specialized, high-performance, scalable, low-cost algorithm hardware co-design, and we want to accelerate multiple steps of sequence-to-graph mapping. Good salesmanship on the paper end there. So what we came up with is this SeGraM. As I said, this is the first universal algorithm hardware co-design. But I believe this was actually the first accelerator at all for graph mapping. And then you can put all these adjectives in their universal co-design and yada, yada, yada. So it supports, the reason we call it universal is that it supports both sequence-to-graph mapping, yeah, this target application that we were looking at, but you can still do the classical sequence-to-sequence mapping with it as well. Reason being, sequence-to-sequence mapping is really just a special case of sequence-to-graph mapping where your graph is linear. And then this works for both long and short reads. As I showed you, data varies quite heavily, but this design is kind of generally applicable. It works for all kinds of data, all kinds of computational tasks. That's why we call it universal. Okay, we show 3 use cases in the paper. So the sequence-to-graph mapping, then just sequence-to-graph alignment and sequence-to-sequence alignment. So we evaluate this quite deeply, and we show performance improvements over baselines in all cases. The key thing here is it supports even other use cases, let's say. For example, you could just use the seeding component of this work also, but there were seeding accelerators before this. What you're seeing here is really the combination that's newly uniquely enabled here. So that you can use one accelerator that can do sequence-to-graph mapping or sequence-to-sequence alignment, whatever you need at the time, or sequence-to-graph alignment. Well, I misspoke somewhere in there, but anyway, you can do all 3 basically. Okay, that was a quick, long introduction. Let me show that idea of the graphs in a bit more detail. So again, here's the classical sequence to sequencing. Yeah, we have a reference genome. It's just a string of ACGTs. So for a human, this is literally a text file with about 3 billion characters, 3 gigabytes. You can download this from the internet and you get really this. You can print this on your terminal or whatever. If I visualize this, of course, this encodes some information like eye color, shape of this guy's face, perhaps some allergies that he has. And then we get reads from this same genome. I'm further visualizing here, and I got rid of the actual data. Then each of these fragments that we get, these reads is 150 characters to up to 2 million, perhaps. The difficulty here is that the original locations are, of course, unknown, so they're somehow scrambled. And the goal of mapping is to arrange them in the way that, well, they correctly belong together. You perhaps saw some illustration of this puzzle analogy before. I think it's a rhino in the other slides. Anyway, you're supposed to map them to align them to the reference. This is if you have a singular sequential reference. There's a bunch of accelerators that do this, multiple from our group. So this is kind of a well-explored, well-accelerated, reasonably efficiently solved problem these days. There's still more work to be done there, still more papers that are showing up, but we're doing a good job at least. We're doing a good job at least these days. But there are some challenges in there still. So we see variants in there. So compared to the previous image, all of a sudden, some of these reads are showing purple skin. You can see an eye up there. And all of a sudden, around the eye, there's purple skin. This is a variant relative to the reference that we have. A reference genome clearly does not have purple skin. The reads that you have has purple skins. Of course, this could be anything, right? Again, this could apply to perhaps allergy that this guy has, or I don't know, if one leg is shorter than the other, those kinds of things might be encoded in there. So when we then map in the presence of such variables, we have some that match well. Okay, so the hand and the color still kind of is the same, or at least similar enough. There's enough context around it. You can see the hand is still purple. Well, it's not purple over here, but there's enough context around it that's correct to still match it exactly, kind of. You still find where it belongs to in the reference genome. So there's sufficient context, but you can still map them. But then you have reads that also fail to be mapped because they're somehow too different. Your variant took up too much of the read. It looks too dissimilar from the reference now, and you either fail to map it entirely to the reference because I don't know, where the hell am I supposed to put this much purple over there? Or you might put it in the wrong location. And if you do find a place to put, I don't know, a purple face, it would end up on the collar, perhaps over here. Just certainly the wrong thing to do. So we call this a reference bias. Somehow we're always doing a better job at mapping reads that come from the exact reference genome that we have. Because it's easier. If you know the exact puzzle picture you're trying to assemble, that's easier than if you only know a distorted version of your puzzle picture. We call this reference bias, and it's a huge issue because we don't have perhaps a reference genome for everyone, and we also don't have a, let's say, fair layout across the population for reference genomes. So, for example, for Europeans or Caucasians, this is we have a good reference genome, but then, I don't know, if you're living in some remote village in Siberia, you might have like really significantly different reference genome, and you would kind of get worse medical care if you cannot properly analyze your DNA. So how do we avoid reference bias? Well, we could just have a whole bunch of reference genomes and then map to it one by one, right? For every person in the world, we have one reference genome, like over here, Now we have the guy with the purple skin over there, and we have, well, multiple versions, basically. The problem is if you repeat the whole process n times for n reference genomes, that's obviously an n times slowdown. You fix the problem, but it became computationally no longer tractable. The second solution is to do this graph-based reference, which means you can avoid redundant computation, avoid redundant data, which also helps with data movement. So everything becomes kind of nice and efficient. And you can even capture some unknown reference genomes. So what you do is you build a graph, you have one reference, and you just encode what's different to that one reference, right? So you say, oh, it's still, I don't know, a vacuum salesman. This is DALL-E's interpretation of a vacuum salesman, by the way. So I told DALL-E I need a vacuum salesman, and then I told it to create variants of it. And what I would store in a genome mapping case here is just same vacuum salesman as before, but he now has a purple skin. Same vacuum salesman as before, but he now has a different type of hand, which is clearly much more efficient than storing an entire separate vacuum salesman. And well, mapping to this is also more efficient. So, okay, this is just a text description of what I just showed you. But let me show you the data representation of the same thing. Yeah, I was still with this visualization slide approach. But let me show you the actual data, yeah, the ACGTs, the representation. So if you have that one original reference genome, it might be ACGT, and then you get the second reference genome that you'd like to encode into that graph. So it has one difference in there, yeah, the T is replaced by a G. So what you do is you kind of split the reference genome into two nodes, and then you insert two alternative paths through there. You can either take the top path, then you have the T, or the bottom path, then you have a G. Now you have a single graph that with minimal redundancy, well, no redundancy, encodes two genomes. Then, well, you have perhaps a third genome that you want to insert. There's another T in there, so you insert another path that encodes this variant. You can keep doing this. And now we're even missing letters, which ends up in a shortcut in the graph. Then, okay, somehow you have to represent this graph in software, but there's a bunch of ways of doing that. That's not too hard. Okay. So how do we map to a graph on the computational side? Well, we have some pre-processing steps. It's really analogous to sequence mapping here. We somehow have to construct that graph, and we have to index that graph. That's offline. We're not too worried about the performance here, at least in this setting. We might be in some settings, but not here. And then we have the online steps that are kind of performance critical that we are targeting for acceleration. Seeding, filtering, chaining, clustering, and the sequence to graph alignment. Okay, I'm showing the data paths here, I guess. Yeah, so we have the offline steps. Out of that, you get the hash table-based index. And then during runtime, you get reads, sequence from some genome, and you analyze them. Right? And finally, your output is some kind of optimal alignment between the read and a sub graph. Yeah. So these computational steps, they're conceptually similar to sequence alignment, but there occur some challenges. Right? Before you had a nice linear reference, kind of is trivial. You literally linearly go through it. It's a simple loop in code. If you implement it in hardware, it's also quite trivial. But okay, so this is how it looks in sequence-to-sequence case. Yeah, the dynamic programming, for example, you have one new entry in the DP table that you calculate comes from one of three entries that you have to consider. Now, in sequence-to-graph alignment, since you have these hops there, perhaps shortcuts or missing edges, now all of a sudden you don't need to just consider three neighbors, but also somehow distant nodes. So suppose you're calculating that table from left to right. Then somehow all of a sudden you don't just need to keep in memory what you computed recently, but perhaps also things you computed some time ago because you need it later again to compute another node. This kind of irregularity makes it a lot more challenging to design hardware and make that hardware efficient. Similarly challenging in software. In software, you can abstract away the graph, but you are left with the performance challenges. In hardware, you then also need to build hardware that can actually deal with a graph at all. Yeah. So that's kind of the challenging bit here. A completely different data representation than we had before. So we analyzed a bunch of software tools and realized, okay, these currently don't cover what we want from graph alignment. So first of all, alignment is the bottleneck. Then observation 2 and 3 basically say it's the memory, stupid. So either you don't have enough cache, and when you then do miss cache, you have a huge DRAM latency issue. And again, kind of related to memory, these baseline tools also don't scale very well with number of threads. And then on the hardware side, so there are existing hardware accelerators for sequence-to-sequence alignment, but it turns out you cannot really apply them to sequence-to-graph mapping. And existing graph accelerators that are for other graph problems also aren't really applicable to graph mapping. So the software solutions can do it, but not efficiently somehow, and the hardware solutions can do some stuff efficiently, but not what we're looking for. So this is SeGraM. We built that accelerator. Well, I'm not sure into how much detail we want to go here, but essentially it consists of a bunch of components that we co-designed on both the algorithm and hardware side. From the algorithm side, we started off this. We started off of this GNASM prior work that I'm going to show you in a second, but we had to add to it a seeding algorithm. So GNASM that, well, I've presented Scrooge to you, which is GNASM++. That does only alignment, but in a full read mapper, you need a seeding step as well. We need an accelerator for that. So we added that to it, and then we needed to extend the GNASM algorithm to also support graphs with this indirect hops, and we had to co-design these things clearly. The algorithms needed to be adapted to the hardware, and the hardware needed to be adapted to the algorithms, as always in these accelerator designs. The details here in the overview aren't too important. Just look at the high-level components. So we have somehow a part of our accelerator that's responsible for seeding. We have a part of our accelerator that's responsible for alignment. That those are attached to some main memory. We need a bunch of memory for our index in particular. And well, we just get input data from the host CPU, and it flows through in a bunch of steps. It keeps going to memory and back to accelerators and scratch pads and so on. And in the end, out we get an optimal alignment back to CPU. Let's look at some of these components in detail. So, for example, this MinSeed hardware, it consists of some logic units, the details of which I'll refer to the paper. And in between each hardware component, we have some scratch pads. So the conceptual design in these algorithms is quite simple in a way that you get data, you write it to a scratch pad. Then you have an accelerator that whenever it's ready to do more work, it loads the data from the scratch pad, does its thing, and writes it back into another scratch pad. Then the next algorithm component loads from that scratch pad, does its thing, and writes it to the next scratch pad. It's a pipeline in a way. So in particular, we don't necessarily need to build one huge monolithic accelerator that, I don't know, tightly integrates all algorithm steps. We can just stick scratch pads in between and abstract these from away from each other. That simplifies things. And yeah, of course, again, we're going to memory all the time, so it's smart to implement these things near memory. Well, there's a bunch of numbers for you. So this other thing I want to show you is the bit-align hardware, is the alignment component in this accelerator. So, and again, as I told you, there's this GNASM algorithm. Yeah? This is literally the GNASM hardware here, which is currently just good for sequence-to-sequence alignment. Yeah, this is prior work from our group. And what we need to do is find a way to efficiently extend this to deal with a graph reference, meaning you have to support indirect edges or non-direct neighbor entries somehow. Yeah, we call them hops. So accordingly, we added a component that's called a hop queue register. Simply what this does is it somehow keeps dynamic programming table entries that you computed some time ago. This is from this earlier table that I showed you, where you're not just using direct neighbor entries, but entries from a few columns over. It means you keep some old data and you refer back to that old data later. So you have some horizon in their history there, but it works for short edges at least. So we extended that algorithm to support graphs, and then we started integrating it into a system. The system meaning many accelerator modules attached to a host across many channels of a HBM2E stack, and then yeah, you can have multiple stacks again. At the end of the day, these accelerators are always multiple levels of parallelism, and then again multiple levels of parallelism on top of that. The idea is, right, you have one tiny efficient accelerator, and then you just use a whole bunch of them to do what you want to do. So at the end of the day, we can use SeGraM for sequence to graph mapping. That's if you use both components, the seeding and the alignment component, or we can just use the alignment component, then we can just support that as a standalone application. Or again, sequence to sequence alignment, meaning the classical problem, then you can also use this hardware. This hardware is no slower on this problem, or you can also just do seeding. Interestingly, this hardware is not any slower, although it's more general. It's not slower than more specialized hardware for sequence-to-sequence alignment. But what you do get is a slight area overhead. Yeah? You're somehow generalizing your accelerator to graphs, which is nice. You can support more things now. But if you are only using sequence-to-sequence alignment, then you could have had a perhaps slightly cheaper, more area-efficient accelerator. I think I'll show you that in a second. Okay, so we compared to a bunch of software baselines and some hardware baselines for the sequence-to-sequence baseline. We took some representative graph workloads that are also used in prior works, and then we started analyzing. First of all, we analyzed the power and area. So what you can see here overall, even though you have like many of these accelerators stacked together, multiple HBM stacks and multiple accelerator modules in each stack across the channels, in total, that entire thing still just draws like 24 watts. It's a huge accelerator throughput, but this is like much less than a typical CPU. The total area is also still quite small, so some 27 square millimeters compared to your desktop PC, which might have like 60 square millimeters or more. This is also on a fairly large node, 28 nanometers. One thing I want to point out here, by the way, is we work a lot in our group with say focusing on memory, one side or another. Now we often focus or we often work on DRAM, but even on chip, actually, memory can be the bottleneck. So what you can see here, out of the entire accelerator, so then let's say one SeGraM accelerator is 0.8 square millimeters, and almost half of that is just scratch pads for that one type of scratch pad. Then you have another type of scratch pad and another type of scratch pad and another type of scratch pad. And actually the entire logic in there, those 0.39 square millimeters, they don't even account for half of the footprint. So even on chip memory that's not that large, you're still spending most of your area and energy on memory. By the way, it gets worse. Actually, if you were to break this green component down further, a large fraction of that is again registers, which you could also consider memory, I guess. So it's the memory. It's the memory, stupid. Right. So we have a nice area efficient, power efficient hardware design. Let's compare the throughput to the baseline. So we have two software baselines, and clearly on long reads, we're getting kind of reasonable speed ups. It could be even more if we had good type of filtering. So let's say smarter algorithms. To some extent, that's why the benefits on short reads are much larger. Here, you don't really have filtering these software tools, strong filters. So you have like hundreds of times throughput improvement while still drawing less power. Okay, and then we have let's see, okay, this is another, I think, software-only tool, if I recall correctly. And then we have the sequence-to-sequence use case. Yeah? So this thing that's supposedly solved quite efficiently already. And it turns out we still have like throughput improvements. So over here we have like 4.8x and 1.2x throughput improvement. The overall accelerator is kind of beefier, but because you have that additional generality of also supporting graphs, you need more memory, you need bigger scratch pads, you need a bit more logic. That means we also draw more power. It's not too bad, perhaps. You might be willing to spend that extra power, but it's a simple trade-off of complexity versus efficiency, let's say. Yeah, and then, well, we have more comparisons which are still showing improved throughput. So in conclusion, well, this is not the conclusion. There's a bunch of more stuff in the paper, including a much more in-depth evaluation. All the algorithms and hardware designs are, of course, explained in detail. But in conclusion, we have designed this SeGraM accelerator, which is a universal accelerator for sequence-to-graph mapping in the sense that it can support both graphs, can support linear references, can support short and long seeds, short and long reads. It consists of those two components. Yeah, this min seed thing, which is just for seeding, that's new. We have bit-align that's built on top of prior work from our group, but we had to somehow adapt it to graphs. And then SeGraM supports a whole bunch of use cases depending on which modules you use with what type of data. At the end of the day, then SeGraM outperforms all kinds of strong baselines, sometimes at some hardware or energy overhead, right? But it's quick, it's general, it's useful. Yeah, so here's our paper. We presented this at ISCA last year. And of course, we have all of our code, always open source. Yeah, that's it. Any questions on this one? While I open up second presentation. Please, go ahead. Yes, okay, let me go back to that. Yes. Is it possible to actually yeah, that's a great question. Oh, right. Thanks. Yeah, so the question was about these HOPQ registers. Yeah, so as a reminder, these are needed to do the dynamic programming computation. Oh dear, many animations before that. Can you find this here? Okay, so we needed that hardware component to essentially store the non-direct neighbors and be able to calculate the fully shaded green entry. And the question was, can we somehow, our hardware unit, well, it doesn't really store everything. It stores up to some, I mentioned some kind of event horizon in a way, right? So basically what happens is our hardware stores up to, I think, 12 nodes backwards. The question was, can we be smarter about it, I guess, by analyzing the graph offline, right? It's a really good question. So I showed to you these preparation steps to mapping, right? It starts with generating a graph, constructing an index, and we consider those offline steps. In principle, there you could, also have some kind of analysis of your graph. That would probably work particularly well if you were to do this in software. The problem is we have a hardware design here, right? So we don't really want to have a new hardware design for every graph that we use as a reference. We want to have a single hardware design that works for everything. So from that perspective, we can't really behave much differently unless somehow our hardware just from the beginning supports maybe multiple nodes or multiple modes of how to deal with these neighbor entries. But yeah, it's imaginable in principle. Certainly what we did do is we have this analysis in our paper. We looked at the human reference genome, or rather a small subregion of it that's well known to have many variants in it. The BRCA1, I think it's called. Basically a fairly complex graph, and we analyzed that to understand, well, how big of a history do we need to support? Yeah, how many nodes backwards do we need to keep? And we came up that with like 12 nodes history, we can store something like 95% of all edges. So clearly, sometimes you have these longer jumps, then you would need to keep more. But yeah, you can try to do this analysis. You can try to optimize according to it. But certainly, there's more headroom to further improve that and be smarter about it. Yeah. Wow. That was a great question. If I can answer for like 5 minutes, no? Thanks. Anything else? Otherwise, I'll switch over here. I can. There we go. Mohammed, what's the deadline? At 30, right? How it should start? Yeah. Okay. This one should be a short presentation. This is RawAlign. We just submitted this fairly recently. Let's see where this is going to be published. But this is basically a kind of finished work. We're building on top of it already. But even though it's not published, let's say I'm confident in presenting this to you. So let me start off with some background. Yeah, this goes in the same direction as this raw hash work that John presented recently. So I'm using some of John's background slides here. So recall these nanopore sequencers. They're kind of these tiny devices. They're mobile, and one interesting bit is that it enables real-time analysis of the data. So when we run them, somehow we have the molecules going through a nanopore. We measure some kind of ionic current that flows through there, which ends up as really a raw signal measurement for us. Yeah? We're no longer dealing with ACGTs. We're dealing with, well, they call this squiggles in the literature. Think of them as plots, if you will, or a floating point arrays. And interestingly, we get those plots in real time. And that's why this slide is so nicely animated. So while they're being produced, we can analyze them already. And if we do it quickly enough, we can interact with the sequencer. We can perhaps stop it while it's still running and save time, right? If we stop sequencing one molecule, we can already start on the next one early before it will have finished. So the earlier you stop, the quicker you can start on another useful one. So latency is kind of a key issue here. Yeah, so we want to have high throughput, but also latency is a huge thing. First of all, then in end-to-end application, not just to make a decision to stop early, we also want to have low latency in the end-to-end application, which kind of is neat. If you can do it while still being sequenced, you can already be analyzing. That means you overlap these somehow. And then if you do this early stopping, that means you can stop even earlier because you don't even need to wait for the full sequencing to finish. So real-time analysis is a new opportunity with this technology. We want to have rapid analysis, meaning high throughput that matches the sequencer somehow. We want to have timely decisions. Yeah? It should be quick in the sense that as the sequencer keeps sequencing, we'd perhaps like to stop as early as possible if we can stop. That's about latency, throughput, latency. Then we'd like to be accurate. Our decisions should be correct. We don't want to throw away useful data and so on. And finally, it should be power efficient. Clearly, if the sequencer is portable, this is like, I don't know, my clicker here is almost the size of one of these sequencers. And it works on USB power. So if that's kind of low energy and portable already, I don't want to carry around a huge server to analyze the data from that sequencer. So basically the new metric that was added in there is latency. Right? We want to be high throughput and low power before. Now we also want to be low latency. One issue we've been seeing is that in these real-time analysis works, they tend to fail to scale. They fail to scale to large reference databases. So for example, the human genome, right, that's some 3 gigabytes of ACGT. Somehow these methods just don't do a good job for these larger reference genomes. They work well for small reference genomes. So for example, a COVID reference genome is only, I think, some 30,000 characters long. And then it's somehow a computational easier problem. And then we have a bunch of good works that do a good job, but not so much for large reference genomes. So our goal here is to get all these target metrics, right? Throughput, low latency, high accuracy, low memory usage, and so on, for a wide range of reference database sizes. We want to have one tool, just give it data and it does its thing. We don't need to specially configure it, whatever. Or even worse, develop a new tool entirely. So this we propose RawAlign. This is the first seed filter align mapper for raw nanopore signals. And it turns out it does a really good job at mapping raw signals to a large reference database with high accuracy, but it doesn't just work for large reference database, it generalizes well. While still having similar throughput to raw hash, it significantly improves accuracy everywhere. Yeah, so just as a reminder, this raw nanopore signal analysis, we get a raw signal out of the sequencer, these squiggles, floating point arrays. Now, with a conventional analysis pipeline, this would be going through Basecalling. So we would convert this to ACGTs, and then you would put this into a read mapper. You get out mapping locations, and you can run some kind of downstream analysis. Then you have an end-to-end application. In the raw signal pipeline, we skip the Basecaller. We don't ever convert to ACGTs. We directly map to a reference. And then we call this a raw signal mapper. RawAlign and raw hash are such raw signal mappers. They directly get the raw signal and produce mapping locations. This first conventional pipeline, it works, it's accurate, but it's costly and power hungry, also not so low latency. Still, for accuracy, it's kind of a good baseline. but it doesn't somehow satisfy multiple of the targets that we have in mind. The real-time analysis, the raw signal baselines we have, they work well. They somehow can directly use all the information in the raw signal, and they scale better. They're less power hungry. Can have higher throughput, lower latency. That's nice, but this is a somehow challenging problem to do well. So as I said, these don't scale too well, unfortunately. We don't have high accuracy for large references. So the reason why this is the case is for small reference genomes, somehow get few candidate regions. So you get a read, you get a bunch of candidates from seeding, and then you evaluate each of those candidates. If you have only a few candidates, meaning you have the reason for having few candidates is you have a small reference database. So there's just not many candidates to be found in there, clearly. Then it's somehow easier to pick the right one among the candidates, and you can also do it at a high throughput because you have a smaller database to search. For a large reference, the key difference is now all of a sudden you have a whole bunch of candidates, right? So think of the COVID example. If you compare to 30,000 characters, maybe you can find a handful of locations where a read might match. But now if you compare to the human reference with 3 billion characters, right, it's like 10,000 times larger reference. Correct? No, it's not correct. Is it 100,000 times? 100,000 times, I believe. All of a sudden, you have to pick the right one among 100,000 times as many candidates, and you have to analyze 100,000 times as many candidates. So it's both less accuracy and reduced throughput. Yeah, more computational load, more energy cost, and well, simply a more challenging computational problem. So large genomes are inherently difficult, and that's why we propose this RawAlign work. And so again, as a reminder, our goal is to satisfy all these targets for a wide range of reference database sizes, but in particular, these large reference genomes, because the small ones are already kind of solved. Well, not solved, but we're doing a reasonably good job at it again. There's always more work to be done, but it works. So if you recall, in the raw hash, we generate candidates using by converting the reference genome using some pre-processing steps to a quantized signal representation, and then we quantize the raw signal in the same way. We apply hashing, end up with a hash table, and then we get out candidate locations. In the case of raw hash, we're done at this point. There's the full mapping. Yeah, you get the hash table, you do chaining and mapping. So if I draw this visually, in raw hash, we have two key steps here. We have seeding, which gets individual small exact matches between the reference on the y-axis and the read on the x-axis. So I drew this simply as a point whenever you have a small exact match between the two. And then what raw hash does is it runs chaining. So it tries to somehow find a set of nicely collinear candidates or anchors. This is also a dynamic programming algorithm, but somehow a coarse-grained algorithm, right? It just has to connect them to each other. It doesn't evaluate what's in between. What we now have in RawAlign, yeah, note the title changed. In RawAlign, we get this alignment step afterwards. The alignment step does a much more fine-grained evaluation. It comes after chaining. And the key idea here is that while the first two steps are somehow relative coarse-grained comparison between the two signals, it works fast. The alignment step is a much more fine-grained comparison, but it's also highly accurate. So if you look over here in this plot, here you just have straight lines. I made them striped to emphasize that these don't really look at what's in between these gaps. It's more about the connection between the points. What you have in alignment is a very fine-grained line here. In fact, that every index here from 200 to 300, yeah, goes in increments of 1. You have a specific point where they align with each other, and you evaluate all those points with dynamic programming. So you compare both sequences to each other in a very fine-grained manner. You check, do they really match everywhere, or where do they not match? Which is more costly to do computationally, but it's much more accurate. So we want to do alignment. There's this, we didn't invent alignment. Alignment has been done since the 70s. It always ends up looking as some variant of a dynamic programming table. Specifically in this case, this is somehow Needleman-Wunsch based. Yeah, you put the reference on one axis, you read on the other axis, and then you have a dynamic programming formula that you use to fill out the entries. So this is a very simple arithmetic calculation. You somehow compare two characters of your read and reference, and then you do simple arithmetic, take the minimum of it. That's your new entry. And as before, 3 neighbor entries, 1 new one calculated. That's what we've been using since the 70s to compare base-called sequences. Note that we're having an exact comparison there between nucleotide bases. Yeah? Meaning you, for example, compare, I don't know, is A equal to C? And if it's equal, you add 0. If it's unequal, you add 1. Is A equal to A? Yes. No cost. Okay. Now, when we work with raw signals, we instead apply dynamic time warping. One major key difference here being that we have numeric signal values. Right? We have 2 floating point arrays. The read and the reference are now not ACGTs, but floating point arrays, meaning if you ever try to work with floating points, comparing them exactly is a really stupid thing to do most of the time. You will almost never get an exactly matching floating point value. What you need to do is have some kind of loose comparison between floating point values. Now you could say, okay, are they within some threshold of each other? But another way to express similar notion of floating point similarity is to just subtract them. Right? Subtract them, get the absolute difference. And then, well, if they're exactly equal, you have a difference of 0. If they're highly dissimilar, you have a difference of, well, if you normalize, you have a difference of 1. Nevertheless, no matter how you exactly score these, right, this is kind of a minor change. At the end of the day, you still have a dynamic programming table, simple arithmetic operations, a minimum operation that's calculated from 3 neighbors. So conceptually, this looks extremely similar. And it makes sense that it would also work for raw signals if it works for base-called sequences. So that's what we did. That's what was our intuition. And well, it turns out it works quite well, actually. There are some challenges in making this work, though. So I told you it's costly to do, right? It's not just costly to align. The alignment algorithms are also called very frequently. So for each candidate, right, I told you about the human reference genome, 3 billion characters in there. And potentially at any of these 3 billion characters, you might have a candidate. Now, these previous steps, fortunately, seeding and chaining filter out many of these candidates, but you still have very many to evaluate. So if you have an expensive alignment algorithm where each call already is expensive and you call it frequently, then you're running into a performance bottleneck. So we took many steps here. Yeah, so I need to amend this picture here. It's slow, unfortunately. So what we did to, oh, right, the reason why it's slow. Such nice animations. The reason why this is slow, yeah, this is just the 3rd step. The dynamic programming table scales with the square of the read length of the candidate region. It's literally a square table of the exact size of what you're trying to align. So this scales with like n times m, right? Which is, well, it works for a few hundred characters, but it's already too much kind of because you're calling it frequently. So we had to take some steps to make this efficient, right? Our first version, when we integrated this into RawHash, it was terribly slow. It was like, it took a few days to just run a simple experiment to check if the idea works in principle. On the same data set that RawHash took 1 hour. So this was not really usable at that point. Nevertheless, actually, we did get an accuracy improvement out of it already. So we at least knew conceptually this would work, but we need to make it fast. So what we did is we used the pre-alignment filtering, chaining, and this is already in RawHash actually. This reduces the number of candidates that you have, the number of times that the alignment algorithm is called. Then we developed some early termination strategy. This another variation of branch and bound. It's a very old idea that's also applied in all kinds of places, including like the Minimax algorithm, yeah, a chess engine. Basically, as soon as you have found a good candidate, you don't need to evaluate things that are already provably worse. So if you have found a really nicely long alignment between the read and the reference, then everything else that's obviously shorter, that can no longer be better, you can just stop analyzing already. This saves a bunch of time. Then you can do anchor guided alignment, basically just align the bits between the red dots that I showed earlier instead of the full square table. You can do banding windowing, which is like going only through a diagonal band of the matrix. It's also an old technique. And then, of course, finally, you can work from the hardware side and implement it very efficiently. So what we did here is we used vectorization, SIMD, to get the most out of the CPU. This is currently not really hardware accelerated outside of SIMD, but in principle, of course, you could replace step 5 here by developing another dynamic time warping accelerator. Wow, we went back by a slide. There we go. We explain all of these in a lot of detail, of course. The paper, there's a bunch of nice algorithm insights in there. And well, I'll show you our code in a second. So we evaluate this on a fairly recent CPU. We used 64 threads for multiple baselines, including RawHash. And then we evaluated 3 use cases. Basically, we ran the equivalent evaluation again that we had in RawHash. To show in a fair manner that, yes, look, in the same setting, this really works well with alignment. Okay, so our metrics that we focused on here were memory footprint, throughput, analysis latency, and sequencing latency. There's 2 types of latencies in here. Basically, the first one is the analysis latency is time spent computing. So how many cycles your CPU is working on the analysis. And then the sequencing latency is how much data do you need. So you have your DNA, right, that comes through the pore. Let this be the nanopore. You have your DNA that flows through the nanopore, and while you're analyzing, this keeps flowing. Now, you'd like to stop this as early as possible if you can make a decision. But nevertheless, you can't really compute immediately. Like, you need some amount of data to start computing and make a decision, right? You need to wait a bit before you even start analyzing. And if you, well, depending on the tool, you need more or less data to make a good decision. So one key metric is how much data does your computational approach need to even start making a decision? That's the sequencing latency. And then finally, we have accuracy, of course, which is kind of obvious that you need to analyze it. We have analyzed on a bunch of data sets, yeah, across a variety of genomes. I mentioned earlier COVID, which is the Smallest of our examples, by the way, there's the genome size, 29,900 base pairs apparently. And the largest one we analyzed is the human genome. Then you have a bunch of mixed data sets to evaluate metagenomic use cases, which is the methodology used in RawHash. Okay, let's look at some plots. So if we plot our 5 metrics as a spider chart here, so each point is one of our metrics, and then you just draw a spider chart. So a larger area is better. The best tool would fill out the entire area all the time. So we did that on these 3 yeast data set for our baselines and RawAlign. And we're seeing quite a nice thing here. RawAlign somehow does really well in all metrics. If you look at the baseline tools, so RawAlign is in blue, yeah. If you look at the baseline tools, let's pick SimpMap here. SimpMap has kind of low analysis latency. It does well in sequencing latency. It has good accuracy, well, reasonable accuracy. But SimpMap, for example, has terrible memory footprint. Now, if you look at RawAlign, it has the best analysis latency, best throughput, best accuracy, not quite the best sequencing latency, but it's up there. And it's also reasonable in terms of memory footprint. And if you look at the other ones, well, RawAlign is the only one that kind of generalizes well in terms of doing well in all metrics. And then, of course, in 2 of the key metrics, yeah, accuracy and throughput, it's doing extremely well. So I just focused on this the three yeast data set here. It's the one we do best at. That's why I showed that one. But nevertheless, we do well at all data sets here. One that I want to focus here on is also these large reference databases. So this is the human and relative abundance use case. What I'd like to point out here is that these really difficult data sets with large reference databases, we don't necessarily have the best throughput. It's not the worst, but it's also not the best. But we're getting really high accuracy. We're getting low sequencing latency, and we're getting low analysis latency. That's important, and it's the only tool that does anywhere near reasonably well on those in those metrics on those data sets. So I think we can claim here that RawAlign does well on all kinds of reference database sizes. Yeah, these are just the numeric results for the same table, by the way. I hope you're happy that I showed you the spider chart and not this. I'll show you one table though here, just a very brief glance. We looked at Minimap2 also for a relative abundance use case. There's kind of an end-to-end use case, a full application using that, including downstream analysis. So Minimap2 is the state-of-the-art Basecalling-based pipe, right? I mentioned it has a bunch of downsides, this Basecalling-based stuff, but what it's good at is accuracy. It's really the state-of-the-art. It's the best accurate way that you have to analyze these things. And we have this distance metric in the last column, lower is better. So what we see is that compared to ground truth, Minimap is off by like 5%. Right? That's the best version we have. And then we have RawAlign, and it's off by 12%. Yes, it's like has over 2x the error essentially. But if you compare that to the best previous, right? RawAlign is based on RawHash. It's making like huge leaps. So clearly this area of raw signal analysis is approaching Basecalling-based analysis really, really quickly. This is the progress that was made in a few months of improving here. Imagine where we can be in a year or two. We're probably cracking the best baseline at that point. And well, what do I say? Probably. There's a chance, at least. There's a chance we can approach that accuracy and hopefully do so at better energy, better energy cost, and higher throughput, lower latency, and so on. Yeah, so that's just kind of a hopefully motivating outlook. All right, yeah, we have, again, all the details in the paper, much more in-depth analysis and all kinds of parameter sweeps and whatnot that you need to understand for alignment. And we have all of our code to produce all those results on our GitHub. So this is a kind of a one-click evaluation there. You could, I think, run 2 commands in there that are very nicely explained in the README, and then it would generate all the results. Now, mind you, if you don't do it with several servers, generating those results will take weeks on your PC. But nevertheless, it starts running at least, if you run it. And if you work with us, well, you can run it on your own on our servers. Hey. Yeah, so let me conclude. We have this problem that raw signal analysis, real-time analysis works, failed to scale to large reference genomes. Our goal was to generalize to all kinds of reference genomes while somehow fulfilling all our target metrics. We proposed RawAlign, this first raw signal mapper that follows the seed filter align paradigm. And we observed that it does well on large reference databases. It's really high accuracy. It generalizes well to all kinds of reference database sizes in all kinds of metrics. And in particular, compared to raw hash, we remain at similar throughput while significantly improving accuracy. And with that, I'm done. And we can continue on with Taha, I think. I can take some questions, of course. Quick ones. Yes. Taha, are you around?
Yeah, I'm here. Can you hear me?
We can hear you. Okay, let me quickly stop the screen share over here. And all right. Yeah, you can screen share now.
All right, give me a sec. Hopefully you should have it now.
Yeah, perfect. Let me. Oh, can you turn on your camera?
Yeah, give me a second. I'm trying to figure that out on this laptop. Where is it? Where's the log? Okay. Okay, now you should have me, hopefully.
Yes, we can see your beautiful face.
Yes, awesome.
Let me. Okay. I think you're good to go.
Okay. Yeah, so hi everyone. My name is Taha Mikhail Shahridi, and today I will be presenting Swordfish, a framework for evaluating deep neural network-based Basecalling using computation-in-memory with non-ideal Memristors. Unfortunately, I couldn't be there in person, so I'm going to present it over Zoom today. And this work has been done as a collaboration between Safari Research Group at ETH, TU Delft, and AMD Research. So with that, let's jump to see Swordfish. Okay, let me see why it's not working. Okay, so let's have quickly look at the executive summary of what we are going to talk about. For the context, Basecalling is the first step as a major throughput bottleneck in today's genomic analysis pipelines. And Basecallers typically use deep neural network, as probably you have also touched upon on the previous talk. We know that DNN-based Basecalling accuracy and throughput will impact the accuracy and throughput of the next analysis. And we also know that prior research uses Memristor-based computation-in-memory to accelerate DNNs, which are similar to the DNNs that we use in the Basecallers. However, the non-idealities in Memristor-based SIM known to hinder the accuracy. So the problem is that the prior frameworks for Memristor-based computation-in-memory accelerators targets large DNNs, but they either overlook the existing non-idealities or they overestimate achievable accuracy by studying non-idealities in isolation or using imprecise models or methodology. They also sometimes overlook the effect of non-idealities mitigation techniques on the achievable throughput. Hence, our goal is to enable accurate and realistic evaluation of accuracy and throughput for these DNN-based Basecallers on the Memristor-based platforms. So our contribution in this work is Swordfish, which is the first framework for Memristor-based computation-in-memory that uses characterized memories and accurate models to solve the two problems that we mentioned. First, to accurately and realistically evaluate the effects of non-idealities on Basecalling accuracy and throughput, and second, to comprehensively investigate the impact of accuracy enhancement technique, particularly on these accuracy and throughput. And our key results show that these frameworks can realistically provide 25 times more or better average throughput compared to the state-of-the-art Basecalling and GPU, and they can improve accuracy loss of these non-idealities by 12%. More importantly, as we discuss later, our framework enables 3 new insights of the future research directions for accuracy enhancement techniques, because as we will see, these techniques are not enough to yet reach the accuracy that we require in these Basecallers. So now let's discuss quickly some background and motivation for this Swordfish. So genome sequencing, which enables us to determine the DNA sequence of an organism, plays a pivotal role in the areas such as personalized medicine, outbreak tracing, like COVID-19 that we just had, and the understanding of the evolution. However, we know that Nanopore sequencing is one of the widely used sequencing technologies. And Nanopore sequencing first converts these DNA fragments into raw electrical signals when they are passing through the nanopore that Joel was just showing over there. And these raw electrical signals then enter the nanopore genome analysis pipeline, where they are converted into a sequence of bases called as reads during the Basecalling. Today, we use these deep neural networks, this cute DNA that you basically see here. I don't know actually if you see my mouse. Let me change that for maybe future. Yeah, this cute little DNA that you see here is the deep neural networks that we use in these Basecallers to perform the Basecalling. This is because DNN significantly outperformed the accuracy of the previous methods. Finally, the output of these Basecallers is used in the next steps, which in this particular presentation, we just call downstream analysis. This Basecalling and the downstream analysis are the Nanopore genome analysis pipeline that we referred to multiple times during this talk. A previous work shows that the Basecalling step, or DNN, can consume up to 84% of the execution time of this entire pipeline that we are targeting. Therefore, from this slide, I want you to have just 2 takeaways. First, Basecalling accuracy can affect the remaining downstream analysis significantly, as the Basecaller is literally the first computation step of this pipeline, and other analyses work on the result of this step. Second, the Basecalling is a major performance bottleneck in our genome analysis pipeline, the number that we just discussed, and needs the acceleration without sacrificing the accuracy, because the accuracy matters in the later steps. And another point to have in mind is that, at least in today's world, Basecallers are just large DNN. And by large, it means that there are multiple levels, many parameters, and usually different types of networks. Now, if we consider our current DNNs, apart from just a Basecalling, outside the context of Basecalling, basically, previous work showed that they are dominated by VMs, which is vector matrix multiplication. And they also incur a significant amount of data movement between the memory and their compute unit, be that a GPU, TPU, or even an ASIC design. We know that from previous works that Memristor-based crossbars support these vector matrix multiplication. And we also know that computation-in-memory or processing near memory paradigm minimize data movement. So there are multiple previous works that I just mentioned here that shows that ideal memristor-based computation memory designs can accelerate the execution of deep neural networks significantly. Now, let's quickly freshen up on some memristor-based crossbars and their support for vector massive simplification, because this is basically the core idea of how to accelerate deep neural network in this work. So the term memristors comes from the memory plus resistance, as we can change the resistance of these devices here and use them to represent our data within the memory. So in this crossbar, we use resistance. We use resistance of each cell to represent the value of weight. And now, if we apply these weights here as a voltages, which represent the value of the input to each row, according to Kirchhoff's law, we can finally obtain a current representing the value of the dot product of the vector input, which are these vectors, and all of the vectors stored in this column. Thus, by modifying just the periphery here of the memristor array and using all the available comments, we can support a vector massive simplification operation in almost one cycle. And let's see how we can do this in a quick example. So assume that we have an input vector, and we want to multiply this vector with a matrix, and we want to get this vector output. So let's first assume that we can program or write these matrices as a resistance levels within into this memristor crossbar that we have. And then we feed our input vector as the voltages to this memristor-based crossbar. Through performing an analog sum inside each of these columns, we finally can convert our output, our analog output, to the digital output, which is going to obtain our output vector. And essentially, we can perform vector massification in just one cycle. So this way, previously we could support, previous work showed that we can support vector massification accurately in the digital accelerators, similar to what we had in the GPUs or TPUs. And now we know that we can also support the same operation in the memristor-based crossbars. So, however, not everything is as clean and ideal as it seemed in the previous slide, as unfortunately our digital to analog converter or DAX circuit might be non-ideal. Moreover, our memristor devices themselves have variations in their synaptic conductances or resistance in which they use to store the data. The wires we use to perform our sum also have some resistance, and they can affect the output since we are using the sum of the resistance within the column. What's happening with this output? And finally, our output should be converted to also digital output using non-ideal circuits for analog to digital converters. And this has to be very accurate because it's considering a whole sum. And this means that in a nutshell, non-idealities are everywhere in a simple crossbar that we just showed. And this means that this figure that I just showed and said it will show how we support vector massification in a memristor-based crossbar is actually just the ideal scenario and assumes the accurate vector massification. And unfortunately, in reality, we cannot achieve this. And instead, we have these non-idealities to deal with, and we should expect inaccurate results for our vector massification if we don't mitigate for them precisely. And this means that our goal in this work is to realistically evaluate the end-to-end Basecalling accuracy, or any deep neural network-based accuracy for that matter, and the throughput on these systems, on these memristor-based SimpP accelerators. To achieve this goal, our key idea is to account for these non-idealities at all different levels of hierarchy. That means at the device level, at the circuit level, and the architecture level. And we have to also account for the overhead of some of the mitigation techniques that have been proposed in all of these different levels, which will impose, as we will show, both throughput and accuracy. So now let's see our proposed framework, which we call Swordfish. So here is the high-level overview of previous frameworks, which has been used for computation-in-memory. So typically, we use to evaluate the effectiveness of accelerating deep neural network on Memristor-based SIMP using these old frameworks. These frameworks assume that either non-idealities don't exist or they do not affect accuracy significantly due to the resiliency of the large neural networks that we are familiar with. They also assume that the non-idealities and their mitigation techniques do not affect the throughput. This is why we call them ideal frameworks from now on. These ideal frameworks took information about DNN and SIM hardware from the user and Memristor-based SIM. Then they feed it to the framework that they have, where the first step maps the network to, sorry, what's happening? Yeah, where the first map the network to different crossbars in the partition and map component, and then evaluate the performance and required area based on the number of parallel and serial vector multiplication in their system evaluator component. However, we extended this overview to Swordfish. And Swordfish do it by two ways. First, we demand more information from the user regarding the device and circuit, as well as some of the optional parameters that we discuss their importance later. Second, Swordfish taking into account that vector matrix multiplication, the core part of any deep neural network, are non-ideal, and therefore a new unit should model their execution. Moreover, Swordfish assume another module should consider the techniques that we use to improve the accuracy of vector matrix multiplication. And finally, Swordfish also assumes that the system evaluator should take these new information into account for accuracy evaluation and performance of throughput evaluation. And this is how we basically connect all the new module and get the more realistic results in our system evaluator. And I want to emphasize that this expansion is very important since our goal is an end-to-end evaluation. Hence, we have to use all the information from the vector multiplication, the basic module in DNNs, to our full evaluation. And now let's quickly look at the first component of the Swordfish, which is our extra component of the Swordfish compared to the previous system, which is vector matrix multiplication generator. As you can imagine, one of the main components is this component. And the goal of this component is to realistically capture the output of vector matrix multiplication when in presence of non-ideal, when we are in the presence of the non-idealities that we just discussed. I want to also say why we are considering the non-idealities at this level, at this vector matrix multiplication level. And this is because this level gives us the most realistic output of what will happen in the future steps. Basically, if you recall the slides about the non-idealities, vector matrix multiplication itself will be the lowest level of the computation in a deep neural network that accumulates all the effects that will happen and will propagate to the next operation or steps in the deep neural network. So Swordfish currently support two approaches to get these non-idealities output. The first approach is to use the measurements from actual Memristor base array in the form of a lookup table. This crossbar has been programmed with the actual weights of our target DNN, which is a Basecaller at the moment, and then output, and its output basically will be the measured results from that actual Memristor when one applies the input voltages corresponding to that vector matrix multiplication. The second approach is to model these errors analytically. By serially applying the accurate models, again, built based on the characterizations to one after another. So you can imagine that the first approach will be the most accurate approach to capture the vector matrix multiplication output in a Memristor-based crossbar, while the second one sacrifices a little bit on the accuracy. And this is because the first approach considers all of these non-idealities and limitations all together at the same time, some of which might actually mask each other or maybe even amplify each other. However, first approach is less flexible compared to the second one and does not really allow you to evaluate the effect of these non-idealities separately. And basically, it prevents you from figuring out which non-idealities you should focus on more than the other. And here you can clearly see that there's a trade-off, and I guess that's a shock for all the engineers, which trade-offs exist. but we can go on with this one at the moment. So we can support both of these approaches in the Swordfish. And now that we know about the vector master simplification generator in Swordfish, let's also quickly discuss the goal of the accuracy enhancer component in Swordfish. The accuracy enhancement component goal is, as its name suggests, of course, to improve the accuracy of vector master simplification. This is done by adopting the inputs and or resistance of memristor devices, such that they compensate the effect of non-idealities and help us to get closer to expected, what is expected, meaning that the output of vector master simplification. So currently, Swordfish supports 4 different accuracy enhancement techniques previously discussed in other works individually. First one is analytical variation aware training. Second is knowledge distillation based VAT. Third is read and verify training. And fourth one is random sparse adaptation training. So I can see that I'm a bit short in time. So basically here, due to time limitation, I want to only briefly discuss our fourth approach, which is also happened to be our most accurate one, which we currently have. But please feel free to read the paper, more about these, like other techniques in the paper as well. So what is the key idea behind the random sparse adaptation techniques that Swordfish supports? The key idea is to not just rely on memristors being ideal, and instead map the weights that are otherwise would map to error-prone memristors to reliable SRAM cells next to them. This way, we can still use the benefit of memristors while mitigating their negative impacts. To make this a little bit more clear, let's discuss the steps that this technique, which we'll call RSA from now on, will take. Specifically, RSA has 3 steps. First step is the initial training that happens on the GPU or the TPU and is one-time task. And then we'll load these weights into the memristors and the SRAM cells. Here, Swordfish requires some inputs from the user, for example, the profile of some of the error-prone memristor devices, to decide which weight should be assigned to which memory type. In the second step, Swordfish performs the vector master simplification operation as usual. However, whenever one or more of these assigned weights to SRAM is involved, Swordfish reads the value from the SRAM memory instead of the memristor-based device. This is easy because one can do this by bypassing the inputs of the corresponding device through the SRAM cell values instead of applying them to the crosswalk. And this is also possible by zeroing the input for that particular memristors in the crosswalk. And then we sum all of these values up in both paths. Finally, in the third steps of RSA, we get the output of the VMM and we use it to retrain our model using any of the offline methods, for example, that was previously shown as a list. And we reload the new weights only into the cells, into the SRAM cells. And this is important because by only applying these, by only updating the SRAM cells, we ensure that we are not touching based on our memristor array. So we are not going to introduce more errors just based on our write variations or our other non-idealities that might happen simply because we are rewriting the memory. So you can find more details about the Swordfish's components and accuracy enhancement techniques in the paper. I listed some of them here for your information, but due to our time, I'm going to skip and jump to some of the results that we have as well. And now let's see, what did we find actually? So here is the evaluation methodology that we have. So we took like one baseline as our base caller, which is the Bonito, is open source, is one of the most open source and accurate like a base callers that's out there. And we also got one of the open source SIM architecture that exists out there. For infrastructure, we use some CPUs and GPUs, and data set and workload. You can find more information about them in the paper, but we basically use the real read and reference genomes with various sizes. For non-idealities and enhancement techniques, we consider all the non-idealities that we mentioned. So we consider the synaptic and wire variations. We consider non-idealities in sensing, ADC circuitry, in DAX and driver circuitry, and a combination of all of these. And these all comes in the second approach of Swordfish modeling the non-idealities in vector mass unification. We also have a fifth version of capturing non-idealities, which is based on the real system. And for accuracy enhancement techniques, again, we consider all of the techniques that we briefly mentioned, and we consider all of them all together at the same time applied to the system as well. So let's discuss the accuracy, which was very important for any Basecaller as they sit in the first step of the pipeline that we discussed. Here is some of our results for what happens to the accuracy when we only consider the right variation as our non-ideality. Note that we assume that we have not applied any mitigation technique in this particular figure. A simple look here should give you two takeaways. First, right variation beyond these 10%, which is the third point in each of these figures, can lead to significant accuracy loss. And second, the accuracy drops significantly and very much varies between the data sets. And this is from 3% to 87%, let's say, in this D1 that I remember. And from this moment onwards, we are going to assume that the right variation, or basically the circuit people or device people, are going to take the right variation under control. So all of the future systems are going to have less than 10% right variation, also in all of the results that we present next. And now let's also look quickly at some of the quantization results, which means that we cannot really map the DFP result or the real default weights to the systems that we have in this like a SIM-based system. So we have to do some quantization. Here we have the accuracy result for default configuration of Bonito presented in this column as DFP 32 by 32. Where the weights and activations are floating point and 32 bits floating points format. And our quantization levels are basically all of the columns here onwards. So we see that two columns can still achieve, these two columns particularly, can still achieve the similar level of the accuracy. And this means that Bonito architecture by itself can tolerate some quantization level without accuracy loss. However, we also see that the quantization beyond a level irreversibly destroy the accuracy to a level that acceleration doesn't matter anymore because we are destroying the result for the next step. So it doesn't matter how quick we are. So now let's consider the accuracy for all of the non-idealities we mentioned in the background, but without any mitigation. And these results that I'm going to present are going to assume a quantization level down to only 16% based on the previous slide, and only with a right variation of 10% based on a slide before the previous one. And these numbers are also based on a few other analyses that we discussed a little bit more in the paper, but I guess we can skip it for the moment. So if you look at these two figures for now only, you can see that the combined non-idealities, either analytically or measured on real chip, lead to significant and I dare to say unacceptable accuracy loss of 18%. This also means that the work or other frameworks that didn't consider these non-idealities are overestimating the accuracy by 18%. So it's not really realistic to consider this for acceleration if your application is accuracy sensitive. But now, if you look at the accuracy after mitigating for non-idealities, you can find significant accuracy improvement regardless of the accuracy enhancement technique, which is still data set dependent, as I have to mention, but consider. From the same figure, though, we can also see that even after applying all of these accuracy enhancement techniques, the accuracy still drops by at least 6%, which is quite significant for a first step, which is accuracy, which is going to affect all of our next downstream analysis. But not everything is as great as it looked in the accuracy part. So let's look at how the throughput look like. So first, let's look at the ideal scenario, which is the first bar in each of these groups that you can see here. We can see that the ideal implementation suggests a 400x improvement on average for Basecalling throughput, which is amazing if you can think about it. But we don't want to stop here, as we just discussed that this ideal implementation come at a high accuracy loss of 18%, which is unacceptable, at least in our case. So now let's look at this throughput figure again, which reveals to us that all the accuracy enhancement techniques drop the throughput, our ideal throughput, compared very significantly, basically. And this is while some of them actually reduce this throughput even lower than the baseline and the GPU. And this is the read, write, verify technique, which led to even worse throughput than just like applying it or running it on the GPU. However, we don't lose hope here, because we can see from the same figure again that our most promising accuracy enhancement technique, which is the hardware software codesign RSA we just discussed, still improves the throughput significantly by 25 times on average, while it also achieves a close accuracy to the baseline, close enough at least, the 6% that we mentioned. Therefore, the acceleration using these architectures, even after the accuracy enhancement techniques, is still possible. So there are more results on the area and accuracy, area versus accuracy analysis in the paper, but I want to show that only 5% of the weight in the SRAM, which is this number here, is sufficient enough to get as close as 5%, 6% to the baseline accuracy for a very simple or small prospect. So I would suggest you guys to also go through the paper and find more about our evaluation methodology and a lot more about our results and observation about the paper. But with that, I want to actually provide some takeaways and summary about this work. So the first and the most important takeaway, in my opinion, is that the target application for these accelerators, particularly on these emerging-based computer architectures, matters, and it matters a lot. And this means that, in other words, deep neural networks particularly do not naturally thrive on these new emerging technologies. And there's a lot more studies to be done here. Second, Swordfish enables realistic evaluation of accuracy and performance for the deep neural network-based application on these emerging architectures. Third, non-idealities are detrimental to both accuracy and performance. So whenever you are talking about processing in memory or processing or computation close to memory, you have to consider the non-idealities that might come with it. And fourth, hardware software co-design techniques mitigate inaccuracy the most. So probably these techniques are the ones that promise us the most hope for the future architectures. And here is a summary of the work that I will skip because I guess my time is up here. So with that, I would like to thank you all for listening to me, even though it was over Zoom. And yeah, I would be happy to take any question that you might have. I hope actually you could hear me through the presentation.
I guess no questions, right? So thanks a lot, Baha,
Yep.
and happy holidays.
Yes, last day of the year.
And thanks a lot, everyone. I think we had a wonderful semester on computer architecture. We wish you all the best and happy holidays.
All right. Thanks, Mohammed. Bye. Have a nice holiday.